Yes. Okay. So good afternoon, everybody. It's a pleasure to be here with all of you again in this seminar we organized. So today we have Professor Sergey Tikhomirov. Professor Sergey works at PUC in Rio, Pontifícia Universidade Católica do Rio de Janeiro. So Professor Sergey did his PhD in St. Petersburg State University in Russia. And then after he did some postdocs and he got some also permanent positions, as we can see in his CV, and he has been working a lot on analysis and fluid dynamics, dynamical systems, now shadowing in PDEs, so very broad fields in analysis. So it's a pleasure, Professor Sergey, and okay, so now it's so up to you.
So thank you very much. The title of the talk is Gravitational and Viscous Fingers in Porous Media. This kind of the main result is a joint work with Yulia Petrova, who is currently in University of São Paulo, and Yalchin Yefindi from Texas A&M. And let me start with the outline of the talk. So first I will introduce the problem, and it would be related to incompressible porous media equation. So one of the topics which pays attention to theoretical PDE, and the special phenomenon of gravitational fingers there. And the reason why I would pose the questions exactly as I pose is that because there is an applied brother problem, which is viscous fingers, and it comes from certain concrete applications like enhanced oil recovery. And even more, I will show how exactly it like this brother problem can be used to optimize the injection during the oil recovery, and it is graded viscosity maps. Yes, and after I motivate exact statement of the problem, I will formulate what I was able to prove about it. So it's not the full solution of the problem, it's a step by step. And so the result, even that the problem is completely from the partial differential equations, result would be more in the style of dynamical systems, as was mentioned in introduction. So this is a broad, it's in a certain sense cross-disciplinary story. So the statement is in the terms of traveling wave solutions, and the proof would be completely dynamical systems. And in the end, I would start a discussion of what are next steps in the problem. So, and at this moment, so if I would be too late in time, you can interrupt me in any moment and we can stop basically at any slide there. And it would be related mostly to infinite dimensional dynamical systems, or might be in conservation laws in a certain sense related to the style of the first talk of the seminar. So let us see what is happening. So first problem, the gravity-driven fingers. So I consider the fluids in porous medium and under the presence of gravitation. And I consider one phase displacement. So I have one liquid and something which is dissolvent inside liquid. You can think about water and polymer. Yes, that's what is used in petroleum engineering. But in any case, it's anything heavy which you have dissolved into water. And I assume that initially you have heavy particles, heavy part of the liquid on top, and the light part of the liquid on bottom. And because of the presence of gravitation, the heavy parts want to go down and light part wants to go up. Yeah, so they want to interchange. Yeah, but there is no obvious way how to do this. Yes, because if it is completely like half of the space is by heavy liquid and half of the space by light liquid, then it has certain symmetry and it has to be preserved. Yeah, so the nature has to find the solution, and solution is the following. Yeah, so what the nature found. Do you see my mouse on the screen?
Yes, yes.
Yes, good. So the solution forms the following pattern. So it appears very thin fingers. Yes, so this is why it is called gravity-driven fingers, and alternating. So there is a fingers of light liquid which goes up, and a finger of heavy liquid which goes down. Yes, so black corresponds to heavy, and white corresponds to light liquid. Yeah, so this is what happens in initial moment. With the time, fingers becomes longer. Yes, and okay, they stop to have such a nice regular picture. They start to be more, I would say, chaotic, and it continues, continues, and continues. Yeah, so this is what is happening, and my goal would be actually in the talk to say as much as I can about those fingers, about how they look like. Yes, and mathematically, what is happening in equations? What equation? What are underlying equations? So there are here three laws. Yes, basically. So I have a variables. It is concentration of heavy particles. And okay, I'm a mathematician. For me, concentration would be between -1 and 1. Yes, because I mean the problem in the end would be shift invariant. So you can add constant to concentration, nothing changes. So for me, it's more convenient to consider it between -1 and 1. The second variable would be velocity of the fluid, and the third pressure. Yes, and there are three equations. One is the transport equation. Yes, so that's with diffusion. Yes, so it's here, it is quite standard. The second is incompressibility condition. So I assume that all the liquid, so that all the only one liquid is incompressible. And the third thing is how I determine velocity. This is important part. And here, this is the moment where appears the word porous media. Yes, because in the talk, I would assume that velocity is proportional to gradient of pressure. Yes, and this is so-called Darcy law, and it is applicable in the case if you have dynamics of liquids in porous media, and it's very common in petroleum applications. I would speak in the middle of the talk how it is used there. But it's not only proportional to gradient of pressure. There is a second force. This is gravitation, and which means that heavy particles wants to go down. So I add here C, concentration. Yes, so concentration, high concentration of heavy particles would go down. Yes, so I can see the two-dimensional problem now. So my domain is two-dimensional. Yes, goes down, and okay, if it is light, then it is go up. Yes, and so you can consider this as an active transport because the velocity u in the end depends on the concentration. So actually those two equations determines velocity in a unique way, and then it becomes, I don't know, active transport equation. So I'm not sure that I use the terminology completely correct, yes, but still it is something like this. And okay, I consider the problem with diffusion, yes, but in mathematics also people consider the problem without diffusion, and I think it's worth to mention it. Yes, so it's like without diffusion, it's called incompressible porous media equation. So comparing to my system, the difference is only here. And for this problem, a huge story is the existence, uniqueness of solution, blow up of equations, because you have transport, you don't have regularized in terms of diffusion, and so it appears a lot of questions. So here I list a lot of work, so well-posedness for smooth data, uh, uh, blow up of solutions. This is the topic which is in the end most related to what I'm doing. So that's sometimes you need to use advanced techniques to define solution like convex integration. And surprisingly, the problem is difficult even in the case which sounds very stable. So when you have light liquid on top and heavy liquid on bottom, and you can see the small perturbation, it happens that it's not so easy to prove that such type of position is stable to the movement. Yes, so that's and all of those, the reasons is that you don't have diffusion, so you don't have any type of regularization. So it is not exactly free boundary problem, but it's of this type. So this is come to here. So, but let me come to my problem back. So when I have diffusion, and the main question which I would consider, so I would consider just one question the most. And this question is the following. So if one looks on the dynamics of those fingers, it would happen that the speed with which fingers grows is constant. Yeah, so the mixing zone, so the zone where both concentrations are present, grows linearly with the time. Yes, and my question would be, and what is the speed? What is the speed of those, of size of the mixing zone? Yes, so how fast it is growing? Yes, and let me first tell what is known about this. So first of all, because this is just one problem, I'm asking about just one number. Yes, so it's not a function, it's a number. So what is the value of this concrete constant Vf? What is known? So for the full model, so exactly as I wrote it here, it is proved that this velocity is not larger than 2. Yes, and this is result by Otto and Manor. At the same time, if one assumes certain reduced model, which has a reason to be considered, so it's heuristically, numerically, they are well connected, it's possible to prove that this velocity is not bigger than 1. And now appears the question, are those estimates sharp? So this is theorems. Yes, this is not numerics or heuristics, so this is theorems. But theorems gives only upper bound. They don't give you exact value. Yes, and at that moment comes numerics. And you can do very delicate numerics, and this problem is very nice when if you formulate it in a Fourier space. And so as was in the previous talk, yes, and in that case for numerics, you can use so-called pseudo-spectral method where you effectively do simulation in Fourier space, and the only moment when you need to come to original space is this calculation of product you see. And then it shows that in 2D, the velocity is the speed of fingers is 0.84. And I cannot say, I mean, numerically 0.84 is analytically 1 or not. I mean, because all the numerics, whatever precise it is, it has errors. So it's not clear. But when, if you do simulation in 3 dimensions, the velocity is 0.6. And 0.6 is much less than 1. Yes? So there is a room for improvement. And this talk and the general research what I'm doing is kind of to find the reason for this improvement. So the new mechanisms for slowing, for determining speed of the finger, so which is different from Otto and Menon. So I would not speak much about Otto Menon results, yes, but I would speak about some new mechanism which was not there. Yes, and so my goal is to find this mechanism and to improve the estimates for the speed as well. And so before I come to this, let me show one mechanism which kind of shows why fingers appears in the first place, and introduce this transverse flow equilibrium model, which is exactly reduced model from Otto Menon. So it assumes that in the solution, the pressure at every point depends much more on the vertical coordinate rather than on horizontal coordinate. And this is, first of all, reasonable intuitively assumption, yes, because the most of the pressure is formed by, I mean, what is on top of you, yes, and on top you kind of have the same. And the second is quite well confirmed by numerics. I mean, of course, because I write here approximately equal, then, I mean, what is the numerical justification of approximately? Yes, clear, but still it is. And in that case, if we are in dimension 2, actually, we can write an explicit equation. So we can replace the last equation, which was the Darcy law, by the following, that the vertical coordinate of velocity is just like here I use the notation C bar. This is average value of concentration along a horizontal line. Yeah, so this minus C, and this comes very easy from conservation law and this assumption. Yes, and the fact that divergence is equal to 0, and if you know the second coordinate of velocity, of vertical coordinate of velocity, you know horizontal coordinate of velocity as well. Yes, so this becomes a closed system of equations. And let us see how fingers appear. So, okay, assume that you have an initial mode just 1 on top minus 1 on bottom, and of course there is no movement in that case, only diffusion is happening. But assume that your initial data is a small perturbation on this. So you have this little hair, yes? And let us see how it would look like velocity here, yes? And if you use this formula and you look on the vertical velocity, so on this small part, C bar is just a bit lower than, a bit bigger than minus 1. Yes, and if you subtract C, then inside of the finger, your velocity will be minus 2 plus epsilon. And on the plateau, it would be just epsilon. So you would have very slow movement up of this border and very fast going down of this finger. And I mean, this is a mechanism how fingers appears. But of course, you never have just one of them, you have a lot of them. So this is why you see this interesting pattern, not just one finger which gets that, yeah, because still the motion is a bit local. Yes, and so this is how one long finger appears. Yes, and so now it's time to come to, before I formulate my results, before I formulate my progress. So let me show what is the applied context. And applied context is, like for me, yes, it's enhanced oil recovery methods. And the same, I was more working with what is called surfactant polymer flooding, but the same problem appears in CO2 storage. Yeah, so this is a related problem. And the idea is the following. So sometimes to extract more oil, you need to inject viscous things inside the oil field. Yes, and this is done to make the displacement more stable. Yes, so it's when you inject it, so you increase viscosity and you can push forward and you can flush out more oil. So let me omit this detail here. But still, this polymer solution is expensive. And you cannot just inject always the polymer because it would be too expensive. So then you inject for some time polymer, and after this you start to inject water because it is cheaper. But by the similar reason as you have gravitational fingers, it happens that if you inject less viscous liquid to a higher viscous liquid, you have a similar pattern, but it is called viscous fingers. Let us see how the process looks like. And so initially you inject polymer into the oil field, and black is without polymer and white is with polymer. And it's initially it is stable, but when you start to inject water again, it appears viscous fingers, and there is a bad moment. The bad moment when your finger crosses this polymer solution, so it's called polymer slag. Yeah, so when it crosses it, so it becomes very bad for oil recovery. Yeah, so it stops the technology, not stops, but dramatically reduces efficiency of technology. And here it happens that the story is similar. Viscous fingers has the constant velocity. Sometimes it's also important to look for a velocity of the back front, yes, because you see the back front is still moving. And there are plenty of works which numerically all in laboratory confirm this. And okay, I cite two my favorite works. One is not by my one, and another is by my one. My one was with co-authors, so was exactly for this situation. Yes, but so kind of the point of this slide that the speed of these fingers is important for application. And this is why, okay, I would dream to have a theorem about polymer fluiding, but okay, I have only some theorems about gravitational fingers. So gravitational is a simplified model for viscous. Yes, and okay, how it can be used. So if you know this velocity, you can calculate the minimum size of the slag, which can guarantee you absence of breakthrough. And if you consider on equations, the first two equations would be the same. The different would be the third equation, which would tell that still velocity is proportional to gradient of pressure, but now you would also divide this by viscosity of your solution, and viscosity depends on concentration. At higher concentration of polymer you have, higher is the viscosity. Yeah, so this is the system of equations. It's very similar. And even that nobody knows exact value of this V, of the speed of viscous fingers, of this VF, still because the problem is very applied, people are using something. Yes, and so there are some simplified models, and so I show them here, it doesn't matter, the idea that they still exist. Yes, and then appears question, okay, assume that you know those, please can you optimize the injection? And one of the ways to optimize the injection is the so-called graded viscosity banks. It is a simple idea. So instead of injecting polymer, yes, of high concentration always, you for some time inject polymer of high concentration, and after this you inject polymer with lower concentration. Yes, and in that case, on each, and only after this you inject water. On each border of injection, you will have a smaller contrast of viscosity, so presumably speed of viscous fingers would be lower, and presumably sizes of slugs should be lower. And yes, indeed it works. Of course, you are not restricted to doing 2 steps. You can do this in several steps. And you can do, like, it becomes not very complicated, but not analytically solvable optimization problem, how to use less polymer, presuming that you use some n number of slugs, and depending on the model, you will have different results. And here is the table, yes, which shows how much you can save the polymer using this idea. But for this idea, you need to know that speed of front finger, speed of back front. I mean, you need to know a lot. Yes, interestingly here, I mean, there is no, I don't know analytical solution for a finite n, but it's possible to find analytical solution when n converges to infinity. Yes, and it's relatively easy formula which allows you to calculate what is the border Yes, so what is the best what you can do with this idea? And surprisingly, and this is what, so this was in a joint work with a Russian petroleum company, Gazprom Neft, yes, and we have a patent related to this. And the idea is that we have a limiting case, and it's surprisingly very close, like just 3 slugs is close to the optimal. Yes, and the practical outcome of this was that, okay, it's not important to use more than 3 slugs, and technologically it's much easier to implement on oil field. So, okay, I know this was a motivation why speed of fingers is important. So now the key idea, what is happening. So if we look on this system, sorry, and let us see how the displacement of viscous fingers look like. This is it. If you look to the fastest finger, you observe that the color there is not blue. Yes, so that's the concentration of the tip of the finger is not zero. Yes, so you have on the tip of the finger still some concentration. And yes, indeed, you can observe this in a more detailed studies of numerics. And what is interesting, that if you presume that you know the concentration, intermediate concentration of the tip of the finger, then there is a not complicated formula which allows you to calculate the speed of the fingers. I mean, we have a theorem which could be considered as an a posteriori estimate. Yes, so kind of if you make simulation and by some reason you were not able to measure the speed of the fingers, but you managed to measure the intermediate concentration, yes, then it happens that this simple, relatively simple formula gives you exactly speed of the fingers. Yes, so kind of this is like a theorem. I mean, this is like a posteriori estimates. And we made strong numerics which confirms this idea. Yes, we did a very delicate numerics of the for this viscous displacement and observed that we have some intermediate concentration here, and this is it's very well aligned with this formula to find the speed of fingers. And okay, ideally, I would like to prove this. I would like to find this intermediate concentration and to prove that the speed is like this. But unfortunately, I cannot do this. And this is why I consider this simplified problem of gravitational fingers. And the results which I have. And now, I mean, we are almost half an hour in the talk, so let us have 1 minute break and just to look on the kitchen science, how you can inject the viscous liquids inside each other in a home environment. So I can see the 2 glasses which are close to each other, and here the white liquid is a viscous liquid and the blue liquid is water, colored water, yes, and you see how nice patterns would appear here, and so you can observe all these crazy patterns which I'm speaking about, not only in numerics, but in 2 natures, but yes, so this is what is happening. So let me come back to the main result. So I would dream to prove something about speed of fingers for this model, but I cannot. So for this, I need to consider further simplification. The further simplification is the following. So if you look on the fingers, they are almost vertical. Let me assume that they are exactly vertical. And that each finger, kind of I would consider it's inside the tube. And inside the tube, the motion is one-dimensional. Yes, and but there is interflow between the tubes. Yes, so it's also allowed. Yes, and in that case, okay, on the next slide I will show the model. But okay, these tubes, or sometimes it's called lane models or layer models. It's I mean, I'm not the first one. who's doing this. Yes, so it's used in combustion, is used for multi-lane vehicle movement, yes, on the roads. But what is more interesting that it also is related to numerical simulation. If you do numerical scheme, and for concreteness, I mean finite volume upwind scheme, but you consider the discretization of the space in a non-uniform manner. So you would consider the horizontal direction divided into a fixed number of cells, and in vertical direction, you will try to make cell as small as possible. Yes, and then, okay, you write your numerical scheme with certain equations, and you can pass to the limit when the size of the cell converges to 0. Then you come to certain systems of PD. Yes, and a certain system of one-dimensional PD. And it would coincide with what I show on the next slide. So there is a second motivation for this. So, but now I come to the description of the model. And so let me see. So I would just copy the equations one by one. So the first is the transport equation. So the transport term inside the tube is here. The diffusion, I replace diffusion only by vertical diffusion. And also there is a cross flow between the tube. So I will speak about it in the end. Yeah, so inside the tube, this is just classical transport equation. I have vertical diffusion, and there is an interflow between tubes. The Darcy law inside the tubes is straightforward. There is a certain delicate moment, the intensity of flow between the tubes. There is no gradient of pressure in horizontal direction anymore. So I consider the difference of pressures in those tubes, and I need to divide by a distance. And because this is not velocity, it's intensity, I'm in the detail, I need to divide by distance squared. And incompressibility condition is that it's obvious, so the derivative of the velocity in vertical direction plus intensity of interflow should be equal to 0. And here, at that moment, I'm ready to define the flow between the tubes. Yes, it's proportional to intensity of the flow, but it is multiplied on the concentration in the first tube if it goes from the first tube to second, and it is multiplied to concentration in the second tube if it goes from second to first. This corresponds to what is called upwind scheme, in numerics. And what is the main result? So this is the system which I showed, how looks like the dynamics. It happens that the dynamics of those systems, now y is drawn in a horizontal direction. So it happens that solution forms a system of two traveling waves. One moves from right to the left, and one moves from left to the right. And now what is more interesting that they goes from -1 to certain intermediate concentrations. From those intermediate concentration, it goes to 1. And this is exactly what we were able to prove. So that's for sufficiently small L, it's possible to show that there is a system of two traveling waves, such that first one goes from -1 to certain intermediate concentration. The second goes from intermediate concentrations to 1. We don't know the values of those concentrations exactly, but we know the limit of them when L converges to 0, and it becomes -0.5 plus 0.5. And here the speed of fingers, don't worry, this is not actually the speed of fingers which would be in a regional model, so you need actually to scale this, and this would be it would be scaled by to 0.5, and if you consider this as intermediate concentration and apply the ideas which we expect to be correct, you will get the speed of 0.75, which is very close to numerical story, but still, but still is too small. Yeah, so We don't claim that this is the velocity of the fingers, but we kind of say that there is a reason that intermediate concentration is present, and that this is not a dream and this is not a result of numerics. So it's a kind of an analytical truth, existence of intermediate concentration. We cannot say this, but we think that this is good enough evidence. How the proof looks like. So that's I will first speak about the strategy, and after this to some details. So we look into the system. It's quite long system, and we do a traveling wave ansatz to find all the traveling waves. Yes, and we get certain dynamical systems. Yes, certain dynamical systems, and it becomes a six-dimensional dynamical system. Okay, let me not go inside the detail. Interesting that the pressures by itself are not important. Important is only difference of pressures, which is natural. Yes, and the traveling waves correspond to heteroclinic trajectories. So kind of assuming that on the one side you have, you're looking for trajectories which are on the one side are equal to -1, and another side to certain constants. Yes, this is what is happening, and in the contrast, what we usually observe when we study reaction diffusion equations, here we have reaction diffusion advection equation. It happens that that such type of condition doesn't uniquely define the heteroclinic trajectory. What we could expect, this is after dimension analysis, is that for any velocity, we can find exactly one value of C1 star and C2 star of those intermediate concentrations, such that there is a heteroclinic corresponding to the speed of traveling wave. And this will say that for front pair, we have a curve of possible intermediate concentration. For the back row front, we have a curve of possible intermediate concentration. In an optimistic idea, so two curves on the plane intersects in one point. And this one point would be exactly the intermediate concentrations which we are looking for. And this is the strategy, and actually it works. Yes, so how it works, this is completely dynamical systems idea. So the two steps. But the first step is singularly perturbed reduction. So I have a six-dimensional dynamical system here, and I look more careful on the pressure part. And after proper rescaling, it happens that it could be represented in such form where L becomes in front of the derivative. Yes, and the right-hand side is kind of capital O of 1. Yes, so this is kind of, it happens that dynamics in pressure is much faster than dynamic in concentration. And this is kind of so-called, like for this, there is a theory of singular perturbed systems. So my original system can be represented in such form where X is concentration part, Y is the pressure part. And so this is the form in which they are. And what we are lucky that the second equation is linear, and the matrix which is in front of this is hyperbolic. So its eigenvalues doesn't have zero real part. And I mean, I don't have a good explanation why it is, but I mean, this is a concrete matrix, so it is like this. Yes, and in that case, it's possible to show that we can kind of formally substitute L equal to 0 here. Yes, and we would have that AY equal to BX is equal to 0. And there is an invariant four-dimensional manifold, which is close to this equation, this one equal to 0, on which the dynamics is happening. Yes, so this is either singular perturbation, slow-fast dynamics, Finish-shell theory, or normally hyperbolic manifold theory. I mean, this is all the class of the object which allows to prove this. And in that case, we can replace the two differential equations here by two algebraic equations here, yes? And it happens that you have that U1 would be equal to C2 minus C1, and this corresponds to this gravitational part divided by 2 plus a small perturbation. Step 1, let's remember, yes? And so we come to a four-dimensional system. Now it's four-dimensional, yes? And let us substitute this L equal to 0 here. And this system becomes a certain concrete system. And very luckily, we can find all its heteroclinic trajectories for any value V of the speed of traveling wave. And I mean, this is a lucky moment. Yes, kind of we have a concrete system of four equations. It is nonlinear, so there is no a priori theory which would guarantee that we can do this, but we were able to do this, and it happens that all heteroclinics lies inside this linear manifold, and you can find velocity, speed of viscous fingers by this formula, and so on. And now what is happening is that what we see is that those heteroclinics actually are transverse heteroclinics. So they have an intersection of transverse intersection of stable and unstable manifold, and so they are able to so they preserve their persistent under small perturbation. And since they are persistent under small perturbation for small l, we would have a small perturbation of this curve. And it happens if you draw those curves. So they form such a rhombus, yes, and the intersection of the curves, which corresponds to the -1, and +1, they are also transverse. So this is how they look like. And after a small perturbation, they persist. And the only moment which doesn't work from all this story to the viscous fingers is this moment. So I can reduce for four-dimensional system. I can consider all perturbations, everything should work, but I cannot find solution for four-dimensional system, even that numerically it exists and it satisfies all what I need. Yes, but still, this is why I cannot pass from the gravitational fingers to viscous fingers. And I think that I'm out of time, so I would formulate only one future problem, which is the most related to the first talk. So one can consider, of course, the problem of not one tube, not two tubes, but several tubes. Yeah, yes, and similar considerations appears, and it's the kernel part of the thinking is this application of it to analog of transverse flow equilibrium model, and it comes, or that it becomes a system of conservation laws, which has the bilinear form. Yes, so this is here it is, and coefficient in front of the spatial derivative is a certain linear function. So it's in non-divergent form, so this is a diffusion term. And where BK is a certain matrices, I mean, this is a concrete matrices, they are not variables. This is concrete numbers, which I have, I don't know, zeros, 1, 2, yes, inside. So this is concrete. They're not easy, but they are fixed stories. And it happens that approach, which I told, works in the case if those matrices by K have a common set of eigenvectors. And it is true for n equal to 2 and n equal to 3, but it's not true for a high number of tubes. Yes, and so, I mean, I believe that this such type of system could be known. I just don't know what is done for such type of systems, and I would leave this as a last slide and say thank you very much for your attention.
Thank you very much, Sergey. Now we open the mic for anybody who has questions or comments. You can also type in the chat. Pessoal, quem tiver pergunta, pode escrever aí no chat ou fazer diretamente a ele. Se quiser fazer em português, ahí a gente puede traducir. Bueno, el que quiera puede preguntar también en castellano, así que el chat está abierto y si tenéis alguna pregunta. Hernán,
Tardes. Sí,
Hernán, sí,
a mí me
Hernán.
interesó mucho. I am very interesting about the patent. About the patent, the patent. I would like to receive some details, description of the about the patent.
Yes, 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 I'm moving there. Yes, yeah,
Is
here.
it the software in MATLAB or in what program you?
To here the details. Yes. So the optimization problem, it is not very high dimensional optimization problem. So if you have n equal, like if you have n number of sleds, it's become a optimization problem in dimension 2n. Yeah, so kind of it's 10, it's not convex optimization problem. So we were solving this in Python. So using this, I don't remember exact method, yes, but I mean it's really not so big deal, yes, because it's not convex, but it's still not very complicated function. So that they were able to find these optimals very, you know, very fast. Yeah, so that's this is not a problem. And the limiting case, yes, it's a theorem. And okay, of course, when you know the profile, how you inject, so it becomes a smooth curve. After this, we have analytical expressions with integrals. And okay, I don't remember how exactly we were calculating integrals, but I mean, this was on the level of Wolfram alpha. Yes, you can just go to the chat. So the interesting story here was that which type of model for the velocities you use. And I mean, this is a very strange story because you should normally you should say, okay, this is the velocity, and I calculate for it. But we calculated, you see, for Koval model, for Todd-Longstaff model, for this transverse flow equilibrium model, which we were kind of pushing, yes. And but because it was in collaboration with a petroleum company, so they were not, we are mathematicians. They not trust to us to choose some model for this because for them it's too much money. Yes. And they actually kind of they usually use the Koval model or Todd-Longstaff model. Yes, so they kind of we do all these calculations for both of them, and the next story was actually supposed to be a laboratory experiment which confirms that all this happens. But in 2022, our collaboration stopped. And so, like, we have a patent, yes, but which is registered in Russia. But I mean, it's very good question, how to check this in experiments. Yes. I don't know if I answered to your question or not.
Yes, but one only question. It's possible to model for the charge transport in polymer like a DNA.
Which transport I haven't
Charge
heard
transport,
that.
electric transport, electric.
Electric. We haven't considered this. I don't know. So the problem. So I don't know if it is related to what the next thing which we were thinking is that how to check. Yes, because you see the picture of concentration of polymer becomes quite crazy inside. Yes. And we were thinking how one can check in laboratory that inside the core happens exactly as what we expect, because in a normal environment you can get, I don't know, pressures in some moments, concentration of outcoming polymer, yes, that's on the outcome. And of course, here I present not, this is not the full details. Yes, of course, you need to take into account adsorption, RRF, and other elements of the polymer. Yes, so here, but I mean, in that case, if I need to do this, I would have to consider more complicated equations. And I mean, all for theoretical investigations, already those equations are complicated enough. Yes, so but we never thought about electricity. Yes, and it would be very interesting. I don't know if I correctly understand your idea that you can look on conductivity depending on polymer. It could help. Yes. Or you were thinking about different type of applications. I'm not sure.
So, last question. Do you have one sensitivity or one polymer? For this case, one example of polymer, and you construct, you elaborate some polymer with this specific condition?
So we did. So here I present only one table, yes, but we did it for several concentrations, several curve of concentration. Yes, so the polymer for our purposes mostly depends on the viscosity curve. So how viscosity depends on the concentration of polymer. So we did it for several concentrations, and here it is a quadratic concentration, which was the closest to a real polymer. I mean, all this was supposed, I mean, all the initial data and so on were considered having in mind a concrete oil field. Yes, and this concrete oil field was very homogeneous. Yes, so there was almost no heterogeneity in permeability, which is important. Yes, and there was a certain polymer. So I'm not allowed, because of the NDA, show the exact curve of this polymer, yes, but what I'm allowed to say that it's quite close to a quadratic dependence of the concentration of polymer, concentration of dependence, viscosity of the concentration of polymer. And this table for quadratic dependence, we also considered exponential dependence, which is more typical for theoretical works. And we also considered linear dependence as a certain limiting case, kind of where this technology actually gives the least help. Yes, so kind of more steep is the coefficient, yes, then more gain you get from graded viscosity banks.
Bueno, muchas gracias. Muito obrigado pelas respostas, don
So
Sergio.
if you are interested, we can speak, more. I'm in Rio de Janeiro, so that's, I hope we would have chances.
No entendí. Viajar, dice, por Río de Janeiro para conocer su trabajo. ¿Eso que está falando? Yes. Okay. Do you have the experimental simulation, this problem, or this polymer specific one? Do you have?
We did numerics. Yes, we did numerical confirmation. We have quite good, I mean, quite well studied, but not published story for the two steps. Yes, so kind of that's where we detailed look how, like, what is happening that if we choose different concentrations for the second step, and it coincides, it confirms with the technology which allows us to get this table. Yes, we did a few numerical results for higher number of banks. Yes, so here is one of the pictures where we have 5 steps. But it's, once again, it's not published yet. And like what I would like to do is the laboratory confirmation, because numerics is nice, yes, but laboratory story would be much, much better. Yes, but in that case, I need collaborator with a laboratory. Yes, I'm a mathematician. I can do the kitchen science. Yes, I can make so the video with glasses which I show, it was done by me and Yulia Petrova. Yes, so we kind of constructed this using some polymer which is used in cuisine. Yes, and, and glasses and some this easier. So
Muito
the easy
obrigado,
options.
professor.
Yeah.
Agradeço muito. Muito obrigado pela resposta. Muito
Yeah, but I
obrigado.
would be. This is actually I'm new in Brazil. Yeah, so I'm here just for 2 years, and I'm very open and I'm very looking for a laboratory partner. Yes, to continue all this stuff. And like polymer is not super relevant to Brazilian landscape, but similarly a problem appears in water alternating gas. Injection. It's in half and puff technology, which becomes popular only recent years, and I'm very open to this. Yes.
Excuse me, the professor is talking about the patent. I would like one question now. In your software of Python, how many parameters you use for the entry? How many
Oh, no, no,
parameters?
no, no, no. Oh, no. The solver of numerical simulation was a C++ program, which was based on a so-called Dumux, so simulator, yes, which is finite volume. Yes, and it was it's quite delicate. Yes, it uses, I think, this one. So the best one which we did, I don't remember, was around 10 million cells, and this was a big job. It's not an easy Python code. This Python code, which allows us to find those percentage, it was easy Python code, and it has a parameter, the model which is used to find VF and VB, and viscosity
Felipe,
function.
eu
Nothing more.
gostaria mostrarle um transporte a ele. Não sei se você me permitir, eu posso lhe mostrar um transporte a ele, que eu fiz transporte elétrico similar em
¿Quieres
Python.
enseñar la pantalla? Okay, Hernán, ¿cómo?
Claro, le voy a mostrar en la pantalla para que él me entienda a qué cosa me refiero yo. Puede ser, si usted me permite, le muestro
Sí,
la
sí, yo
pantalla.
creo que sí. Juan, ¿se puede?
Share, share.
Juan,
También. A
¿puedes
ver,
dejar?
share también, share. ¿Send request? ¿Está? ¿Envía
Sí,
pantalla no? ¿Yo?
no,
¿Ya puedo presentar o no?
no sé cómo. Juan,
Presentando aquí, ya Zoom,
Hernán
application,
quiere
¿cuál es?
enseñar algo.
Screen. Screen, ya screen, share screen. A ver, ¿se ve la pantalla ahora?
Sí, ahora sí.
Mire, lo que yo estaba, I could like to explain for you que in Python, I have elaborate transport electric in Python for the polymer. For polymer de DNA, like so your presentation, Matt, you see in this program, I have introduced some parameter for this problem. Display the electric, the probability to have the charge transport. In one position, I have electric transport. That is my question. For in Python, have this result. Show me for you. This is a Python for transport. I would like to show in Python transport. In this case, is electric transport.
Okay, no, so kind of you speak about a slightly different application, yes? And here my answer is the following. So the viscous, so I didn't give an overview, yes? But viscous fingers appears in a lot of stories, yes? I mean, it's not exactly viscous fingers. It's not exactly those, but very similar. It appears when you consider lightning exposure from the, I don't know what is during the rain is happening. It can appear in tumor growth. Yeah, so that's, I mean, you can look on these similar equations when you consider the blood flow via capillaries, yes, in your body. I mean, of course, there would be different type of questions. So, and I don't pretend that, my result is applied exactly there. But I mean, the general philosophy is still similar. I don't know about electric transport, so I never studied this, but I would be very interested to know more.
Okay, thank you very much. Okay, thank you.
Yeah, thank you. Very, very, very interesting. Yes.
Okay, so
Thank you very much.
so maybe I can finish here because we had a bit on time. So if anybody has another question or comment, a quick one, so we can chat. If not, let's thank again Sergey, and Sergey, thank you very much. Our next section will be on August 6th